So what we are going to study today, actually start today, is basically an algorithm which is by now already well known. Probably you have heard the name, or some of you might have uh, utilized it already. I don't know. Any of you have already utilized this genetic algorithm? Okay, no answer. So I will assume it as no. So okay, so this is basically not among the class of the classical optimization tool. Rather, it falls into the category of meta heuristic algorithms, where basically there are two terms. Meta simply means it is beyond heuristics. So the heuristic algorithm, it has certain pattern of solving the optimization problems, but meta heuristic goes a step further by introducing some sort of randomness or stochasticity. So you can call it that addition of randomness in heuristic optimization algorithm. Some example of heuristic optimization could be like the greedy algorithms. Okay, the family of greedy algorithms. We're not going to discuss or not going to go into the detail of that. So what we are interested on is this family of algorithms. So in the last class at the starting, actually I mentioned what are the disadvantages or limitations for gradient descent algorithm. Can anyone remember?
Like if there is any discontinuity, we can't.
Yeah, if there is any discontinuity or the function is not differentiable, if these kind of things occurs, then the gradient based algorithms, they suffer to give us a solution actually. So in those cases, and in many other cases, like for example, where the solution, the exact solution, I should say, to find out the exact solution of an optimization problem is going to take, let's say, infinite amount of time. I should say infinite. That means it is not solvable within a finite time. So in other words, I can say that it is going to take infinite time. In the field of optimization, usually that is called as NP hard problem. Okay. So NP, simply you can call it like non-polynomial in time. That means the solution time is not polynomial. And it is very hard to solve. Okay, it is very hard to solve. So there are actually other families of this NP kind of thing. Like there is P, simply P, NP, NP complete, and the final one is NP hard. And the complexity increases along this direction. P means it is a polynomial in time, means if you start to solve it, if the number of variables increases for your optimization problem, the decision could be taken, or the optimization solution could be obtained within the polynomial function of time. And this one is non-polynomial, so maybe exponential, and this one are a little bit more complex than the first two. So if your problem is such that one of the category could be like this, the exact solution of an optimization is going to take enormous amount of time or computational effort. Next, if the optimization scenario is such that you are satisfied with some near optimal solution, you don't need the exact solution, rather some near optimal solution is good enough for you. So in these cases, we may adopt the meta heuristics or heuristic algorithms. And there are a family of this, okay? And among this family, one family is called, among all these families, one of the families is named as evolutionary programming or evolutionary algorithms. And within these evolutionary algorithms, one of the most famous one is genetic algorithms. So by now it should be clear where and when we might require this application of genetic algorithm, okay? Where the gradient search might fail, or where if you are trying to find out the exact optimum solution, it is going to take me a pretty long time, okay? Or I am satisfied with some near optimal solution, okay? I don't need the exact optimum value, rather any near optimum value is fine enough for me, for my design problem. So in these cases, we can resort to meta heuristic algorithms. Okay, so now this algorithm was actually adopted from the concept of natural evolution, okay? Because as the name says, you will find the evolutionary concept, and the concept says, in short, it says survival of the fittest. So this is the mantra for the evolutionary algorithms, or specifically for the genetic algorithm. Means if you are fit, you are going to generate new child with respect to time. So your progeny will continue. And the person who is not fit enough, he will not be able to survive, and his progeny is going to be finished very soon. Maybe another generation, or his generation is the last one. He is not going to produce any more progeny of him. Okay, so the survival of the fittest, this is the main point. So now let us see what are the steps actually involved in the genetic algorithm. Okay, each of the algorithm under this meta heuristic, these are mostly taken from natural inspiration from different natural phenomena, and genetic algorithm is taking the phenomena from the evolution, natural evolution occurring in, let's say, population generation or generation of any animal or any plant in this earth. So so what are the steps and what are the terminologies that would be required for understanding the basics of genetic algorithm? Let us go through that one by one.
Sir, is this a PhD thesis?
No. This is simply an introduction. This is not a PhD.
Oh, it
Don't
looked like a
worry.
thesis book, sir.
Don't worry. This is not a PhD thesis. Actually, what happens, there are probably some conferences where they accept the chapters. I mean, they accept the paper and they put it in the form of a book, published books. So probably this is that kind of scenario where you are finding this abstract written here. Okay, so don't worry. This is not a PhD kind of thing. This is very simple thing. And
No, I thought any student devised this algorithm during his PhD.
No. This was actually developed by Mr. Holland, John Holland, long time ago. Okay, this is nothing new.
Okay,
this
sir.
is nothing new. One of the oldest in this field of optimization, one of the oldest. And interestingly, there were some problems actually. Before the advent of genetic algorithms, it was very difficult to solve those problems without the help of this genetic algorithm. I mean, with the help of the classical optimization problem, it was taking, I mean, pretty big amount of time for getting the solution out of those. Probably you have heard those names. One of the algorithm or one of the problem, optimization problem, famously known as the traveling salesman problem, TSP problem. Another one is 0-1 knapsack problem. I don't know whether you have heard these names or not, but these are very interesting problems. So I don't want to go into the detail of this, but the TSP problem is basically one sort of ordering problem. By ordering, I mean, let's say you have some cities, okay? And these are the cities. A salesman who is traveling, he has to complete his path. Let's say city number 1. Cities are represented by simply nodes 1, 2, 3, 4, 5, and 6. So the problem statement is such that each city, or at least some of the cities, are connected, if not all. And between each city connection, there is a certain weight or cost associated with each of the connection. Okay, let's say 1 to 2, 2 to 6, 1 to 3, and several weights are given for each of these. Okay, let's say something like this. So as you know, the weights or the costs for the traveling from one city to another, and these are the nodes 1 to 3 up to 6. 6 cities is to be traveled, and the salesman has to start, let's say, from any of the cities, from any of the 6 cities available, but he has to complete his travel touching all the cities and without crossing his way whenever he is traveling, and without repeating a city. Okay, repeating his appearance in the city. That means what? If I just erase the connecting weights, so that means the scenario could be something like this. So he can travel, let's say, from 1 to 2 to 3. He has to only touch each of the cities so that he can sell his products. So if he travels in this manner, he can complete his round without repeating any city more than once. Have you got the idea?
Yes, sir.
Okay. But this is only one of the many possible solutions, isn't it? So there could be other solutions, like, can you now take part in this game with me?
1, 4.
Okay, 1, 4, but make sure you don't cross any line. 1, 4,
Okay.
and you don't repeat any point more than once. Of course, you can come back to the origin.
Okay, 1, 4.
1, 4.
5.
This was 3, 5.
6.
6.
3.
3,
2.
2, 1.
I think I just reverse it.
Okay, no problem. No problem. That could be another solution. Okay, like permutation. That could be another solution. But of course, for these two traverse, the cost will be the same, right? Because it is simply the reverse one. So cost will be the same. Why I'm saying cost? Because I said each of these connecting paths has a certain weight or cost. So ultimately, the traveling salesman is looking for the minimum cost for his travel or for his journey in a day. So this is known as the traveling salesman problem. Simply you have to order your reaching of each of the nodes one after another. So this is one sort of ordering problem. Okay, you have to order or sequence, ordering or sequencing, you can say, sequencing problem. Okay, so this was one of the problem which was taking a lot of time and a lot of effort was required for solving this kind of problem before the advent of genetic algorithm. When it came into the market of optimization, the problem was solved very, very quickly compared to the earlier algorithms. Okay. So this was the traveling salesman problem. Another problem is the knapsack, 01 knapsack problem. The 01 knapsack problem is the story of a thief who somehow has got into a big shopping mall, and he has now the choice of picking up some stuffs. However, he has some constraints. So he has a bag. Let's say this is his bag, some sort of bag. I'm not a good artist. So let's say this is his bag, which he is carrying. A backpack. Let's say this is a backpack. And there are items. Of course, when a thief comes to a house, he should try to maximize his item that he is actually taking, right? Stealing. So let's say in the market, he finds a jewelry, flower bags, electronics, accessories, and so on. So the 0-1 problem in knapsack says either you have to pick it or not pick it. If you are picking it, then it is 1. The weight is 1. If you are not picking it, actually it is multiplied by 0. Okay, this is 0-1. Now what is the constraint? The constraint is there is a maximum weight the thief can carry after his stealing period is over. Okay, so this is his constraint, the maximum weight. This is the constraint. There is a maximum limit, and his target is to maximize the cost of item that he is stealing. You get the idea? So now he has to decide whether he will go for jewelry, how much of that he can take, whether he will go for flower bag, what is the cost in the market when he goes for selling it in the out market, which electronic equipment is he going to take, and of course he has to keep in mind that he has maximum value of his weight. So he cannot go beyond the weight, and he is looking for some maximum output out of his project, okay, stealing project. This is the 0-1 knapsack problem. This is another problem which was taking or killing time of the programmers or the optimization engineers. So genetic algorithm came and helped this cause of solving this 0-1 knapsack problem. Okay, so these are some of the examples where genetic algorithm was used earlier at the beginning. If you want to look into further detail of these two interesting problems, you can Google it. You will get probably a lot of literature available on this.
Previously, you mentioned about one YouTube channel, some Irani guy, most probably.
That is Mir Jalili, Syed Ali Mir Jalili.
Oh, sir, Mirja.
Let me write the spelling. Syed, he writes it together. So Syed Ali Mir, in Bangla probably we call him
Jalali.
Mir Jalil, not Jalali.
Okay, sir.
Mir Jalili, Jalil, Mir Jalil.
Okay, sir.
And generally they end it with I, like our African brothers, they end it like O and U, Mahmudu, Mohammadu, and something like Osmanu. Okay. So this Iranian guy, he finishes with I. Okay, so Syed Ali Mir Jalili is actually one of the pioneer researcher in the meta-heuristic domain in the current world. So if you are interested in applying this kind of knowledge in your research field, you can go through his lecture. He has a channel in YouTube. You can always go through that. Okay. So I have probably gone through a little too far from genetic algorithm. So let's come back to the track. And what are the key terminologies associated with this genetic algorithm? Let's start. So the components and terminology. So these are the key components associated with the genetic algorithm. So let's start from number 1. What is the fitness function? What is fitness function? This is nothing but the same as the objective function. We all know what is the objective function. So there is nothing new with respect to the first point. A population of chromosomes. Why these terms are coming? Because this concept of genetic algorithm is actually borrowed from the biological process. So you will find some terms which are used in human generation process, the biological process, not only human, any living being. For any living being, these terms of chromosome, genes, alleles, there will be some terms. I will explain them as I go through those. So what is a population and what is actually the chromosome? So the initial genetic algorithm, the first during the advent of genetic algorithm, that was actually, you can classify it or you can name it as the binary coded genetic algorithm. Okay, binary coded genetic algorithm, where each solution. Okay, another thing is that before I go into this BCGA, another thing is that the meta heuristics or the heuristic algorithms, unlike the gradient descent algorithm, they will start, I mean, the genetic algorithm, let's say the genetic algorithm as an example, will start from multiple initial solution point. This is a key difference. Multiple initial solution. If you have gone through my last lecture, you remember we were talking about x naught and x1. You remember? Minus epsilon del L. This was the formula for updating the vector of solutions. Inside x naught, there was PG10. You remember? PG20, PGN0. So we were only taking a single solution to start with. Okay, we were initializing the initial point or initializing the gradient descent algorithm with a single set of solution or a single set of initial point, which was the vector x naught, and we were updating only that solution for in each iteration of the algorithm with the help of epsilon and with the calculation of the gradient del L. Unlike that, here we will be starting with a set of initial point or a set of solutions, probable solutions, set of probable solutions. We call that family of solutions the population. Is it clear? What is the population? Yes. Okay, very good. And each each solution is termed as the chromosome. Okay, so a collection of chromosome is basically the population in genetic algorithm, a collection of chromosome. Okay, probably when I take an example it will be more clear. Don't worry. Okay, so we will have some chromosomes, and of course, as I was talking about the binary coded genetic algorithm, in this case your solution or the chromosomes are to be encoded in the form of string or the binary bits 0 and 1. So let's say for any optimization problem, if you say, let's say if you say, well, my variable x, it is a single variable problem, let's say variable x, the probable solution is, let's say it can vary from x, the variable, single variable optimization, it can vary from 0 to 15. Okay, there is a function, let's say x square by 2 minus 10, something like this. This is your f of x. This is your objective function. So if you are looking for the encoding of your population or of your chromosome actually, so let's say your population, you want to start with population size 10. That means you will start your genetic algorithm with 10 different probable solutions. Each of the solution can take any value between 0 and 15, not anything less than 0 or not anything higher than 15. So how many bits would you need for encoding it in binary? 4 bits.
4 to the power.
Okay, 2 to the power 4 minus 1. So that will cover 15 bits. 15, yeah, 15 different combinations. So that means if you take 4 bits, you can cover from 1111 to 0000. Okay. So this is your how much? 1111, and this is 0.
0, and that is E, that is 15. That is
15. So you see, in this manner, by knowing that how much is the range of my probable solution x, I can choose the number of bits that is required to represent those things in binary encoding. So this is the encoding part. Okay, this is binary encoding. So now why I am writing it, it will be clearer because I want to actually explain what is chromosome. So let's say I have taken pop size equals to 10. That means I can have any value from 0 to 15, and from that range I will choose 10 probable solution. Okay, so let's say let's make it smaller because we don't have enough space. So let's make it 6 just to make life easy. So the pop size or the population size is 6. So let's say if I continue it like this, so pop size 6. So let's say the first one is 1010, second one is 0010. Arbitrarily, I'm writing it arbitrarily: 1110, 0001, 1001, and 0000. Okay, are they distinct? Hopefully they are distinct. So now this is my population. This is my population. Size 6. So 6 different chromosomes. So this is one chromosome, this is second chromosome, and so on. Clear? What is chromosome and what is population? The whole thing is population. Individual solution is chromosome. Okay. Now next, inside the chromosome, let's go now a little bit further. Let's take any one chromosome because we need to look further. Let's take this chromosome 1110. This is one chromosome. How many bits? 4 bits. Each bit location is known as the gene. Okay. The value inside a certain location is known as allele. So this is location number 1, gene location 1, gene location 2, gene location 3, gene location 4. Okay, these are the locations are gene. The values inside that location is allele. Okay. Now there are another two terms. One is genotype and another one is phenotype. So genotype is when we are considering the chromosome, this encoded representation is the genotype. And its actual value, how much is the actual value?
842.
12.
14.
842, oh yeah, 14. The last one 1, so it would become 50. So genotype is this encoded term, and the actual value is the phenotype. Okay. So these are some of the terms you might come up when you try to go through any work done with the help of GA. Okay, any question up to now? Still now nothing difficult. I think it is very easy. Okay, so then the next thing, actually the next question should come to our mind, actually how we are going to generate these chromosomes, okay, within the range. So if it is the binary coded genetic algorithm, then simply the job is done by flipping a fair coin. I mean, let's say you have a coin. At one side you have the head, another side you have the tail, and the probability of head coming up or tail coming up for a certain toss would be exactly same. This is known as uniform coin. Okay.
So can we consider then fraction, say x, we consider 0 to 50?
That is continuous domain. That topic I don't know whether I can cover it today, because it is although there are very small number of slides maybe that is going to be covered from this PDF, but actually because it is new to you, so I would go very slowly at the beginning. That is continuous GA. That is the next topic actually, not here. I mean, not in article 1, probably in 4 or
So
5.
this time we'll only
section.
consider 0, 1, 2.
Yeah,
like
this is binary coded genetic algorithm. This is for discrete optimization, not continuous optimization. Continuous would be a little different than this. Okay, we will not going to, you are not going to use the binary encoding there, encoding or decoding. Clear?
Okay, sir.
Don't worry, we'll go there inshallah. Unfortunately, it is not an optimization course, so I wouldn't take too much time here. I will only just go through the basics of this. Okay, so where we are. Okay, so how we are going to generate this, let's say 6 population or 6 chromosomes. Simply for each bit or each gene, we are going to toss a coin. Okay, so either it would be a 1 or a 0. Either, and for next toss, because for each one I have to toss it how many times? For each chromosome, 4 times. So the first toss yielded 0, second toss yielded 0, third toss yielded 1, fourth toss of the coin yielded 0. So this is my first chromosome. Got the idea? So I have to repeat this sequence of tossing up the coin how many times? This many times. Clear? 6 times. The whole,
Yes, sir.
so that means 6 multiplied by 4 bits, 24 times I have to toss the coin for generating the initial set of population or initial set of chromosome. Done. Next, let's move on. Remember, here I am only considering a single variable problem. I am not taking more than one variable to start with. Later on, I will show how to do the same thing for more than one variables. Okay, just to keep things simple. Okay, so then now this one is done, this one is done. Come to the third one, selection of which chromosomes will reproduce. So now that you have known your chromosomes, what were those? 0, let's write it down arbitrarily. 1001, 0011, 1100, 0100, 1001, 0000. Okay, and let's say your fitness function is something like this. Okay, something like this. This is your fitness function. How would you select which of these chromosomes will reproduce? Means this is my first generation of solution or initial set of solution, of course, in the encoded form. So what I can do before going to this step, what I can do, I can simply calculate the fitness values for each of these chromosomes, isn't it? So what is this? 1001. How much is this?
9.
9. How much is this? 3. This one, 12. This one, 8. Oh, there is a repetition.
4.
No. Oh, this is 4?
Yes, sir.
Yes, sir.
Okay.
4.
This is 4. This is actually a repetition. So let's make it. Okay, let's leave it for the time being. Repetition. No problem. And this is 0. Now, of course, I can calculate what is my fi of x, isn't it? Where I is 1 up to 1, 2, 3, 4, 5, 6. I is 1 up to pop size. Clear? I can have an array of fitness value now at this stage. So if you have the calculator, you could have gone, you may go through that and you may give me some values quickly. Yeah, if we have 6, if we are 6, okay, including myself, so you can take each one of you can take one and give me the value, so it will be quicker.
We should consider x is equal to 9, x is equal to 3.
Yeah, simply like that. Simply just give me the value.
So I'm taking the last one. 0.
Okay, I could have taken it. So you are the winner in this case. So remaining parts. Okay, Farhad, take another one.
Okay,
You can,
I'm
you can take
first
9
one.
because yeah,
Okay.
this will take care of 2.
Sir, I took 4, but the answer was 0. I don't know.
Okay, excellent. So you have 0. Nice. The first one is not 0. Sorry, the last one is 0.
First one
Sir,
is
4. I
-45.
took 4.
Yeah,
Number
yeah.
4.
4 would be 4. How
12
can
is minus 48.
4? Sorry, which one?
12 is minus 48.
12
Yes, sir.
minus 48. Then first one.
-8 -45 by 2. That is minus 22.5.
22.5. Second one. Anyone took it? Hey, Ghazi, did you take anything? Probably he's outside.
No, sir. Yes, sir.
So 1.5 for 3. It should be
Okay,
1.5.
1.5. Okay, so now you see we have very interesting values here. Some values are positive, some values are 0, some values are negative. We haven't mentioned actually our target. In general, genetic algorithms are used for maximization problem, but it doesn't mean that it cannot be used for minimization problem. So because you see what is the the slogan for this? The slogan is survival of the fittest. So that means you are looking for some maximization effect, right? Some positive effect, not some negative effect like minimization. So from the basis of the origin of the genetic algorithm, you're looking for some positivity. So that's why in general you can easily use it for maximization problem. However, you can also modify the fitness function itself to apply it for to apply GA for minimization problem. So for the time being, we will stay with the maximization of this function. Okay. So now with our initial generation, what is the best fit individual or best fit chromosome from this one, if it is a maximization problem? So let's write the rank. Let's write down the ranks. So which one is the first one? This is the first one, right?
1.5.
So that belongs to this one. So this is ranked 1, first ranked individual initially. Then
And then 0. So there are 2 zeros there.
so this is 2, joint rank 2. Then another 2, 3, because they are actually
Yes,
same, and 4. Okay, so out of 6 actually we have got 2 ties, but this is only arbitrary case. Okay, so this is my initial set of solution or fitness value. So where we were actually discussing how do you select the chromosome, which chromosomes are going to take part in generation of next progeny. So the next progeny would be, okay, so the chromosomes that will take part in generation, or we call it reproduction, the chromosomes that will take part in reproduction are known as the parent chromosomes. The resulting chromosomes would be treated or known as offspring in some cases, some places, or the synonym is simply child. Okay. So now we will be looking at the step how we are going to select the parents first, who will take part in the reproduction phase. Means what I am going to do, I am going to simply update this array. Okay, that is known as the reproduction. But the question is, how am I going to do it? So the easiest way, or one of the ways actually, there are many ways. One of the way One of the ways is to look at this fitness and put much weight or higher probability for those chromosomes who has higher fitness. Let me repeat. In the reproduction phase, for selecting the parents, what we are going to do, we will put higher probability of selection for fitter individuals or chromosomes. Remember, individual and chromosome are the same. Chromosomes or individual, like a single person, you can say, for fitter individuals. Okay. So that means the chromosome or the individual which has higher fitness should get or should be picked with a higher probability for regeneration. And that is actually the motto. The motto or our slogan was the survival of the fittest, right? So the fittest one should be able to produce more children or should be picked up for reproducing at a higher probability, with a higher probability. Is this point clear? This is the main motto of selection procedure. Selection procedure. Selection for what? Selection for reproduction. We haven't yet gone to the reproduction stage. We are only talking about how we are going to select the chromosomes which will reproduce. So the lesser fit chromosomes should not take part at all or should take part at a lesser extent, okay, or with a lesser probability in reproduction. So one way to do this is simply calculate the probability of the ith individual. Let's say small p. Probability of the ith individual is simply f of I, that means fitness of the ith individual, divided by the total fitness. I equals 1 to maximum how many? 6 fi. Okay. So you'll see that if I follow this simply this formula, then I will get a probability chart with some specific probability across each of these fitness function or each of these individuals. And you will clearly see that, well, if we can get the formula calculated or get the formula done here, then the probability you will find that for the highest rated or highest fit, best fit individual will be having the highest probability. There is a small problem here because probably I have chosen the fitness function arbitrarily. So what we can do, we can keep the fitness to some positive value for the time being. Otherwise, there might be some problem in finding out the probability, because you see the probability cannot be negative. But because of these symbols, there could be instances where you might end up with negative probability. This is only because I chose this fitness completely arbitrarily. You get the point? Probability cannot be negative, but you might end up with some negative values there because of my arbitrary choice or arbitrary selection of fitness function. But this formula, I will show you how they are applying it in tabular form. They have solved an example. So don't worry. I'm just giving you the steps here, the flavor, how we are going to proceed with this. So now, is this concept clear? How we are going to calculate the probability and how we are going to select the chromosomes who will reproduce. I haven't finished actually, so let me continue. So after finding out the probability, what we will do is we have to identify how many children we are going to produce at first. Okay. So now tell me how many children you are expecting out of these 6 chromosomes. I mean, in the next generation, how many individuals you are expecting to be present here?
3.
3. Okay. Anyone? Okay, this is a guess, no problem. These are guess, so don't worry. You can guess any value.
4.
4. Okay. Then
So depending on the rank, like you are talking
no,
about the
I said how many total individual you expect here. How many children you want? Do you want only 1 children, or 4 children, or 5 children, or 3 children, or 6 children, or what? Okay, for the time being, the answer is I want actually the answer is variable. Okay, the answer is variable. It's not so straightforward because there are different techniques to fill up the blank spaces. But one thing is common, that is the total number of individual will remain same throughout each of the generation. So if I have 6 individuals here, my total individuals will be 6. Okay, this is one thing. Next thing, how many children and how many parents will remain here? So there is this is where the difference lies. So some policy says, well, I will make it 50-50, means I will keep the first 3 most fit, or the topmost 3 fittest individual or parent, and I will drop the remaining 3 or remaining 50%. And then I will make reproduction among the remaining 3 to fill up the remaining 3 blank spaces. This is one way. But we are not going to go with that way for the time being. What we are going to do, we are going to replace all parents. We are going to replace all parents which are present in my first generation or in my initialization step. Okay, so I am going to generate 6 children for the time being. Is it clear? Later on, we will see that we can also go for 50-50. 50% we can keep, 50% we can remove, or there are many other options actually. So one of the 2 options I have only mentioned. You can change or update all individuals from the first generation or the immediate generation, previous generation, or you may change or update all entries, 50% or all. These are the 2 options that I am sticking with. But now I am using 60%, sorry, all. I am updating, I'm going to update all. Okay. Now the question is, now the question is, how am I going to do it? So I know the probability. So what I will do, I will now take help of a concept known as the Roulette wheel selection. Have you heard this name? This is only one of the many ways for selection. Only one of the many ways. This is actually available in the casinos. Okay. So how does it look actually? It will give space it will give space to a certain individual or a certain number appearing on the overall wheel, depending on its fitness or depending on its probability. So if that is the case, then which one should take up most of the space, even without calculating the probability for the time being? Which one is the fittest? 0011, right? So 3 would take highest chunk of the portion. Who is the next one?
second rank.
Yeah, second rank. Who?
0100 and 0000.
Okay, tell me the values. I mean the
4 and 0.
decimal values, 4 and 0. So they have lesser space than this, 4, and they should have equal, right? So in this manner, actually, probably my proportion is not 100% correct. So in this manner, Roulette wheel will provide spaces for certain individual on its body. Is it clear? So the lowest one would be which one? 4.
9.
9. Okay, probably 9. No, there were 4, I think. 1, 2, 3. 12. 12 is the 48. You see, 48 minus 48.
Yes, sir. Yes, sir.
So this is 4th. So this will get a smallest proportion. Okay, this will get a smallest proportion. Sorry, this is 12. So this one is 12. And in addition to this wheel, there is a pointer, fixed pointer. Okay. So what is done? A person, he or she rotates the wheel at a certain or at an arbitrary speed, and the portion or the chunk that is being pointed by this pointer at a certain rotation will be awarded. This is actually the Roulette wheel policy. Okay. Have you got the idea? So, should I repeat? So if you rotate it, let's say if you rotate it, maybe my chunks are not drawn to the exact drawn to the scale. So let us make it look like a big 3. Okay, this is 3. Then probably this is 4 or 4 and 0, and then smaller ones are 9, and this one should be smaller. Okay, now have you got the idea how the distribution would be done?
Yes, sir.
Okay, now probably it is almost up to the scale. And there is a pointer, fixed pointer. A person is going to rotate the wheel, and then after a certain time, what is going to happen? The wheel is going to be stopped, right? And a certain number is going to be attached to this pointer. Clear? So now it tell me, because of the probability, higher probability of 3 taking the most portion of the chunk, most portion of the wheel, 3 has the largest probability to be adjacent to the pointer, isn't it?
Yes, sir.
So this is how it works. So in this manner, actually, the Roulette wheel selection process will give you 6 children. Okay? Or sorry, not 6 children. Sorry.
Parent.
Let me repeat. Sorry. Yeah, I have a call. Okay, sorry, I made a mistake. Actually, the parent. Okay, I'm looking for the parents. So in this manner, the parents could be repeated, because this selection is basically done with replacement. Those of you who have taken probability course, they should know what is meant by with replacement and without replacement. With replacement simply means you have, let's say, 3 balls, 2 white and 1 black. And what is the probability that you pick up if you pick 3 times, or let's say 5 times, what is the probability that the black ball would be picked? And here, of course, you have to consider with replacement. That means when you pick a black ball, you see the basket becomes empty of black balls. So with replacement means you are simply replacing the black ball again with the one that is being picked, so that you again have the probability in any of the next pick, you can again pick the black one. This is with replacement. Without replacement means when you pick up the black ball, it is done. It is devoid of any black balls. So there is no further probability. You get the idea? What is the difference between with replacement and without replacement? So with replacement means if in one rotation of Roulette wheel, if you pick 3 ones as a parent, then in the next rotation 3 will be again replaced. That means 3 will be still there. You are not taking out 3 altogether after the first pick. This is meant by with replacement. You replace 3 again. Okay, so that means there is a chance of a parent to be selected more than once. Am I clear?
Yes, sir.
Very good. So how many times you have to rotate the wheel to pick up the parents?
3 times, as you said that we will take 3 parents and 3 children.
No. Parents, children will come out of the parents. So now actually we are preparing the mating pool. Okay. So I have to take, because I am going to replace all, remember, I am going to replace all individuals present here. I am not keeping 50%. Remember, I'm sticking with the plan or with the selection process that all my individuals are going to be updated. So for selection, I have to rotate it 6 times. Okay. Remember, I have to rotate it 6 times because 6 is my total number of individual or the population size. Clear?
Yes, sir.
Okay. So this is Roulette wheel selection. There are of course other selection or very popular selection selection algorithms or ways. Another one is tournament selection, but I am not going to discuss in detail for that because Roulette wheel is being used here in this book, but there are other ways. Okay. So next, selection is done. Probability calculation is done. What is next? We have the crossover. Okay. Now we have chosen the mating pool. We have made the mating pool. And let's say the mating pool is something like this. Who has the next highest? Can anyone help? Who has the next highest probability? 0, right? 0 was 4. Okay. Then, okay, 0 is another one. It has the same probability. 3 has highest probability. This is purely I am picking on my own. You know, this is on arbitrarily picked. Of course, I'm trying to put more emphasis on those who has higher probability. What is the least probability? We just leave it. We just leave 12 for the time being. The least probability of being picked. And we are left with, what is the other one?
Minus 22.
1001.
9,
Maybe.
right? Yeah,
Yes.
1001. And we are left with another one. Let's make it again 3. Okay. So this is your mating pool. This is the mating pool. So this is the new set who will take part in reproduction. Clear? So let's erase it for the time being. Don't have enough space. So this is my mating pool. So how they will meet or how they will mate? Using crossover. Okay. So there will be 2 parents, one father and another one mother. If you want, you can label them like this, but there will be crossover. That means now you see the beauty of the genes. Okay. What happens? Let's say this is your father and this is the mother. Okay. You see, these are the genes, right? These are the genes. These are the genes, individual locations. And now they will take part in crossover operation. This is one part of the reproduction, one phase of the reproduction. Reproduction has now started. So now there will be crossover, and there are many different ways of crossover. One of the ways is simply known as single point crossover, which I am going to show you. Single point crossover means what? Means you are going to choose a random crossover point, a random crossover point. So in this random crossover point, what you are going to do for each mating or each pair of mating between each pair, you are going to generate a random number between these locations, 1, 2, and 3. Okay, there are 3 positions: this position, or this position, this position, or this position. Okay, so there are 3 positions where you may have some crossover. How does it work? Let us see. So let's say you run a random number generator from 1 up to 3, and it comes up that for the first meeting you get first point. Okay, the single point is sometimes also known as K point. This is general, more general name: single point, 2 point, and there are actually more than 2 points also, depending on, of course, your length of the string or length of the chromosome.
Sir,
Yes.
sorry for interrupting.
No
If you
problem.
allow me, I have one meeting from 9:30, so I have to leave. But before that, I have contacted with Shimul Bhai. He is on the road now. He said that 16th February at night is okay for him.
Okay, then if it is okay with others, then we set it to 16. Okay.
So is there anyone who has any issue with this date? So sir, then it's final.
Okay, then 16th is final. Then we will try to sit before that for
Okay, sir. So it
maybe I will take another class on Saturday. When is your first exam?
Monday. I'm sorry.
No.
Officially, it should start from Monday. That is
For you, unofficially, what was the first date?
okay for me.
স্যার এখনো প্রথমটা আমার ঠিক হয়নি, এখনো মাই ডেট দেয় নাই কবে
Okay.
হবে।
I actually wanted to take another class on this GA so that I could finish the example at least available in this book. Otherwise, probably you will forget everything after, if I delay the class after mid-exam. That is the problem. So if you allow, we can take another class, which is supposed to be taken on Friday. But Friday I have to attend the office, so I would like to have it on Saturday, this coming Saturday. Of course, if you agree. Otherwise, no problem. The problem is at your end, you will forget everything what I have just mentioned. Okay.
Maybe we can inform you.
Yeah, no problem. You may discuss among yourselves and you may inform me. No problem.
So sir, Wednesday at which time? 7 p.m. exam time?
Actually, the exam is going to be 1.5 hours. So 7, I think, would be pretty early for that guy, Samuel. You will return from office and then he will sit for the exam. Let's
Yes.
make it at 8:15. Problem?
Yes, sir.
Yes, sir.
9:15, 9:15, then 9:45. I think that is good enough. 9:45 is good enough. We can have the dinner after that.
Okay, sir. I will inshallah inform Shimul Bhai and also post it in
Yeah.
Messenger.
Yeah.
Okay, sir.
Okay. Thank you.
Assalamu alaikum.
Walaikum assalam. So we're actually almost at the end of the time. So let me finish at least crossover and then mutation at least. Then in the next class, inshallah, we will see the examples. So the single point crossover actually chooses a single point arbitrarily or randomly at for each mating. So let's say this is K equals to 1. So then what will happen? This 3 and this 3 will actually be swapped. So this 3 will go here and this 3 will come here. So how will the children look like? So 0, 1, 0, 0, and then this one would be 0, 0, 1, 1. Okay. So interestingly, in this case, actually, there is no change. You see, there is no change. Okay. But this will be the children. We will take it as the children, which is the same as the parents, which has the same traits or same features or same genes as the parents, even after crossover. However, if we took the crossover point to any different location, then we might end up with different children. Have you got the idea of crossover at least?
Yes, sir.
Okay, so you pick a point randomly for each meeting, for each pair. Let's say we pick the pair from the top, but this choice of pair can also be a random process. Okay, but I am just showing you sequentially. We are picking the first two as the pair, next two as another pair. So you see next two 0000 and 0011. Again, we have to run another random number generator from 1 up to 3, and we have to pick a point. So if you pick a point, which one? Let's say
Middle point.
no.
2.
If we pick the middle point, there will be again no change. So we have identified it. So intentionally, I have taken this point number 3. Okay, so that at least we can have some update. So in the children phase, what will be the result? 0 0 0 and 1 will be there.
1.
So now you see you have some difference. 0 0 1 0.
1
So now
0.
you have two different children with respect to the parents. Okay. For the next two, you do the same. So how many children you have? 1, 2, 3, 4, and another 2 will come from these two. Okay. So that means you will end up with a new set of chromosome, isn't it?
Yes, sir.
So you will get 0 1 0 0 0 0 1 1. This is number 1, number 2, then 0 0 0 1, number 3, 0 0 1 0, number 4. And let's say there could be also a possibility that there is no crossover at all. Okay, that would happen if you choose your point K from 0 to 4 instead of 1 to 3. 1 to 3, I'm just picking to pick up any intermediate point. But if you choose the random number from starting from your position 1, not 0 actually, position 1 up to position 4, that is the length of your chromosome, then you might end up with a number, random number, which is 4, which is here. Okay. So in that case, there won't be any crossover actually. So let's say we simply copy and paste the last two just to save our time. So this is my new, or not completely new, this is my chromosome after crossover. Okay.
Yes, sir.
Now can you calculate the fitness? You can, of course. Okay, we haven't reached at that stage, but at least if we calculate the fitness, you might find, we don't know, we might find some better fit individuals or some better fit chromosomes at this stage. So this is after crossover. The last stage, which is pretty shorter compared to all the previous steps, that is mutation. And that is done to introduce some genes or some traits or some features within the children which is or which was absent in both of the parents. Means what? Means now you want to add some more diversity in your solution or in your population. How we are going to do that? As I said, that feature of mutation, what it will do, if it is a BCGA, binary coded genetic algorithm, simply it will do what? It will flip the bits. It will flip the bits. So there are two steps in mutation. Choose the position or choose the chromosome where mutation has to be done. Choose the location of the mutation and then perform the mutation. So this mutation operation is done at a very low probability rate. Let's say at the rate of 0.001, very low probability. This is the probability for mutation. So in this case, you don't do it for all, let's say, all individuals present in your population. Rather, you do it, let's say you run a random number generator, 0 from 1, 2, 3, 4, 5, 6, from 1 up to 6. And for each generation, you pick, let's say, only one of them. Okay, only one of them. Or in some generation, maybe not any of them. So randomly, pretty randomly, with a very low probability, you choose an individual. Let's say we choose the second individual, and we choose again a specific bit or a specific gene position, gene location, or gene. The gene itself is the location actually. So a specific gene to be mutated. So let's say we choose this one and this position. So what will be the outcome? After
Once-
mutation, yeah, after mutation, your population pool would be, the first one will remain same. Next one is mutated 0001. Others will remain as it is. But that will happen very rarely, okay, with a very low probability. This is mistake. 0010 1001 and 0011. So this is your, so this is where you have, actually I have erased everything, 001, and this is the mutated bit, and this is your new solution set after the reproduction. So in the reproduction we have two stages. The first stage is crossover, second stage is mutation. Before this, what we have to do? You have to do selection. How you do it? You calculate the probability following this formula for each individual, and then you follow the Roulette wheel selection. So then after you mutate, you get the generation 2, next generation population, and you recalculate the fitness, recalculate the probability, redo the selection, the crossover, the mutation, and the loop will continue until you fulfill the stopping criteria or until you reach the convergence. Okay. So I'm not going to elongate my lecture anymore. I'm going to stop here. So the topic is probably new for most of you. I hope you have got some interest after this discussion in this genetic algorithm topic, which is a very famous algorithm still today. But of course, I am discussing the very basic part of the genetic algorithm, or very basic structure of the genetic algorithm. There are many variants of it. Okay, there are many variants of it. So the next class, inshallah, I will continue with this same topic, and we'll be actually following solving an example or few examples. Okay, that would be more interesting. So any question? Any question? No question. Okay, that's good. So okay, please discuss among yourselves, and if you agree, then we will take at okay, only one class before meet. Okay, that is the replacement class for the Friday. Okay, then, so I will share the recording inshallah in the Google Classroom. So till our next class, stay safe. Assalamu alaikum.
Assalamu alaikum.
Wa alaikum assalam.